Okay, let's unpack this. We are about to venture into what is really the true control room of your physical existence.
Hmm.
Today, we're doing a deep dive into the system that regulates everything you are, everything you do, and everything you feel, all without you ever, having to file a request or hit a switch.
We are dissecting the autonomic nervous system, or the ANS.
Mm,
And, if the human body is the most sophisticated machine ever built, the ANS is kind of the internal autopilot.
the autopilot, I like that.
It keeps the engine running, constantly fine-tuning performance. It's controlling all your involuntary, non-negotiable functions.
Mm.
So the rate and force of your heart, the smooth muscle lining your blood vessels and organs and all your glands.
And that distinction is just so crucial for anyone new to this, because most of the time when we think about our nerves, we're talking about the somatic nervous
That's
system.
a voluntary one.
Exactly, the one we control. Deciding to use your muscles to pick up your phone or walk across the room. The ANS, it operates in the shadows, completely beneath our conscious perception.
Exactly. You don't consciously decide to increase your blood pressure or constrict your pupils. The ANS handles all of that, minute by minute. Its entire reason for being, its core mission, is maintaining homeostasis.
Homeostasis. Okay, that's one of those big words. Can you break that down in practical terms for us? What does that really mean?
Think of it as a dynamic equilibrium. It's not static. It's a constant, active process. The ANS is continually monitoring thousands of data points: blood acidity, oxygen levels, your temperature, heart rate,
Everything.
and it's adjusting things to keep them within a very narrow, healthy range. So if you stand up too quickly, the ANS corrects your blood pressure instantly so you don't faint.
Right.
If you eat a meal, it reroutes blood flow and activates your digestive enzymes. It's the ultimate invisible regulator.
And I think most people have a feel for the system through its most dramatic mode of operation, the classic analogy,
Oh, yeah.
fight or flight.
That's the star of the show, for sure. And it's a system that's older than our entire species.
Mm.
Just, think back to the savannah. You encounter a threat, maybe that lioness we always talk about.
Mhm.
Your body doesn't need to consult a manual,
Right.
right? It needs immediate, total mobilization now.
And in the modern world, that lioness is just as likely to be, I don't know, a stressful deadline or your boss looking for weekend volunteers.
Why?
The physiological response is ancient, but the trigger can be totally modern. So let's detail that activation, the sympathetic response.
So when the sympathetic division fires,
Yeah.
it's an all-or-nothing system-wide event. It's like the body is hitting the nitro button. The main signaling molecule, adrenaline or epinephrine as we call it, floods your system.
And that just prepares you for
Bang.
massive exertion.
Exactly. Your heart rate soars, your blood pressure shoots up to push all that oxygenated blood to your big muscles, your legs and arms.
It's fascinating to me that you actually start sweating before you've even moved a muscle. Why does that happen so fast?
It's pre-cooling. The body is anticipating the massive heat that running or fighting is about to generate.
Ah.
So the sweat glands activate to prevent overheating. It's a critical piece of the survival puzzle.
Mm.
And meanwhile, inside, your breathing gets deeper. That's because the bronchi in your lungs dilate, we call it bronchodilation, to get more air in.
More oxygen. And you get that change in your vision, too. It's subtle, but it's there.
Yes, your pupils dilate. The technical term is mydriasis. The goal is simple. Let in as much light as possible, maximize all the visual information hitting your retina. You're trying to track a predator or find an escape route. Every little bit of data helps.
And this whole coordinated response, this is why, in the modern world, chronic activation of the system basically is anxiety and stress.
It is. The body is constantly primed for a physical threat that never actually arrives.
That sounds absolutely exhausting. You can't stay in that fight-flight state forever. So
Yeah.
how does it pull the emergency brake?
Well, that's where the opposing division takes over. The parasympathetic response. It's universally known as rest and digest.
Rest and digest.
This is the state that allows for recovery, for repair, and for absorbing nutrients after the emergency is over. The brake gets slammed on, heart rate slows, blood pressure comes back down, and most importantly, the digestive system, which was completely shut down during the sympathetic rush, gets the green light to turn back on.
So if the ANS is this constant push and pull, the sympathetic versus the parasympathetic, to achieve that balance, well, that sets up our deep dive perfectly. We know what it does. Now we have to understand how it's wired.
Absolutely. And our goal for you listening is to provide a really thorough step-by-step understanding. We're going to peel back the technical jargon and actually look at the physical wiring of the accelerator and the brake. Then we'll look at their chemical language, the neurotransmitters, and then the reflexes that govern it all, and finally, which parts of your brain are ultimately calling the shots. We'll try to make the anatomy make sense by focusing on the story it tells.
Okay, let's start with the accelerator then, the sympathetic division. We said it's all about this massive system-wide signal, mobilizing everything at once. Structurally, where does this command actually come from?
It all starts in a very specific, limited area of your spine,
Mm.
and that gives it its technical name, the thoracolumbar system.
Thoraco, lumbar. So thoracic is the chest area, lumbar is the lower back.
Exactly. It means the central command neurons that kick off the sympathetic response are only found in the lateral horn of the spinal cord, specifically from the thoracic region, T1 down to T12, and then the upper lumbar regions, L1 down to about L2 or L3.
That's a surprisingly small slice of the central nervous system.
Yeah.
So how does a signal that starts just in the chest and upper back manage to reach, literally every single part of the body? My eyebrows, my toes, everything.
This is where the wiring shows its genius. It's designed for widespread dispersal. So the output fiber from the spinal cord, we call it the preganglionic fiber, it projects out to these specialized distribution hubs, ganglia.
Bingo.
And the most famous of these is the sympathetic chain ganglia.
Can you paint a picture for us? What does this chain actually look like?
Okay, so picture two long beaded chains running straight up and down, one on each side of your vertebral column. They're like parallel strings of pearls. We call them paravertebral ganglia because para means alongside the vertebrae.
Okay.
And there are typically about 23 of these little neuron clusters on each side running all the way from the base of your skull down to your tailbone.
Now, wait a second. You just said the command only comes out from the T1 to L3 section. So if the signal only leaves from the middle of the back, how do the parts of the chain up in the neck, the cervical part, or down the pelvis, the sacral part, how do they get activated?
That is the key mechanism. It's divergence. The central neurons in the thoracic and lumbar spine send branches that travel inside the chain itself. They can go up like a neural elevator, ascending to reach the 3 cervical ganglia that control your face, eyes, and salivary glands. Or they can travel down, descending, to reach the 4 lumbar and 4 sacral ganglia, which handle your pelvic organs and the blood vessels in your legs.
So traveling inside the chain is what allows one signal from, say, T1 to ultimately affect something way up high. It's what makes it a massive, coordinated, body-wide response.
You got it. That's how it works.
Okay, so the sympathetic chain handles things that are generally near the spine or up in the head, down in the limbs. But what about that huge network of organs deep in your abdomen? The gut, the kidneys, the liver.
For those, the signal uses a second, separate set of distribution hubs. We call these the collateral ganglia, or prevertebral ganglia.
Prevertebral, so in front of the vertebrae.
Exactly. They're located anterior to the vertebral column, out in the abdominal cavity, much closer to the organs they serve. The most prominent one is the celiac ganglion, and its job is basically to coordinate the entire sympathetic response for all those big abdominal organs.
This sounds really complex, but I guess it simplifies to 2 distribution systems. You have the chain, which goes up and down, and the collateral, which goes forward into the gut.
That's a great way to think about it.
Now let's talk about the wires themselves, the fibers, because there's a huge difference between the input and output wires here, isn't there?
Absolutely. The sympathetic system is defined by its fiber lengths. The incoming water, the preganglionic fiber, which runs from the spinal cord to the ganglion, is relatively short.
Short because the ganglia are close to the spine.
Right. And crucially, these short fibers are myelinated. They have a fatty sheath of insulation, which makes the signal travel extremely fast.
And these myelinated fibers are the ones called the white rami communicantes, right? White because of that fatty myelin.
That's the one. And that speed is vital for a survival response. Now, the output wire, the postganglionic fiber, has to travel from that chain ganglion all the way out to the distant target, the heart, the eye, a blood vessel in your foot.
So it has to be long.
It has to be much, much longer. And it is unmyelinated.
So the rule for sympathetic is short, myelinated preganglionic to a long, unmyelinated postganglionic. And these long, unmyelinated ones exit via the gray rami communicantes. Gray because they lack the myelin.
Precisely. This whole structural setup, short pre-long post, combined with all that branching, is the anatomical reason why the sympathetic response is so rapid, so divergent, and so systemic. One central neuron can light up dozens of targets almost instantly.
Speaking of rapid and systemic, we have to talk about the ultimate exception to the wiring rule, the adrenal medulla.
This is such a beautiful example of evolutionary efficiency. So normally the preganglionic fiber synapses on a second neuron, the postganglionic one.
Right.
But at the adrenal medulla, that's the core of the adrenal gland sitting on top of your kidney, the preganglionic fiber projects directly to these specialized cells called chromaffin cells.
So the chromaffin cell, it basically is the postganglionic neuron.
Functionally, yes. But instead of releasing its chemical onto a specific target, the chromaffin cells dump enormous amounts of epinephrine and norepinephrine, the hormones we call adrenaline, directly into the bloodstream.
The whole gland is acting like a sympathetic ganglion.
It is. But its output isn't a wire, it's hormonal.
And why is that hormonal output so critical for fight or flight?
Because it guarantees maximum dispersal. It's systemic. Neural signals are incredibly fast, but they only travel along the specific path of the axon.
Right.
Hormones travel through your circulatory system. They reach every single cell in your body at the same time. It's the difference between sending a targeted email and broadcasting an urgent global announcement. The nerves start the immediate local changes, like heart rate, but the hormonal dump ensures that body-wide sustained mobilization you need to survive.
Okay, now let's clip to the break. The parasympathetic division. This is all about localized, precise control, the rest and digest mode. Structurally, how is this different from the sympathetic system?
Well, again, the origin defines the function. The parasympathetic system is known as the craniosacral system.
Sacral. Okay, so cranium is the head, sacrum is the tailbone, the two extremes.
Exactly. Its central neurons are located at the two anatomical ends. In the brainstem nuclei, that's the cranial part, and in the lateral horn of the sacral spinal cord, S2 through S4, that's the sacral part.
Okay, so the sympathetic ganglia were all clustered up close to the spine. Where are the parasympathetic distribution centers?
The location is completely flipped, and this is a really key concept to get. Parasympathetic ganglia are known as terminal ganglia.
Terminal as in at the end of the line?
Exactly. They are located very near, or sometimes actually inside, the target organ. When they're inside the walls of the organ itself, like in your intestine or your bladder, we call them intramural ganglia.
Okay, so if the ganglion is sitting right next to the target organ, what does that mean for the length of the wires? It has to be the opposite of the sympathetic system.
It's completely reversed. Since the brainstem or sacral spine is far away, the preganglionic fibers are very long. They travel almost the entire distance to the target.
And so the postganglionic fibers must be
Super short. They only have to bridge that microscopic distance from the terminal ganglion into the target tissue itself. This long pre-short post setup is what allows for such precise, localized control. The signal is basically delivered right to the doorstep.
Let's trace one of those long pathways. What about controlling the pupil of the eye?
Okay, so that uses cranial nerve the third, the oculomotor nerve. Its central neurons start way up in the brainstem, in a place called the Edinger-Westphal nucleus. These long fibers travel to the tiny ciliary ganglion, which is right behind the eye.
Right.
And from there, really short postganglionic fibers cause the circular muscles of the iris to contract, which makes your pupil constrict. A very precise local response for highlight conditions.
And then there's the undisputed highway of the parasympathetic system, the one that governs pretty much the entire torso, the vagus nerve.
The vagus nerve, cranial nerve X, is the heavyweight champion. It carries about 75% of all parasympathetic outflow. Its fibers start in the medulla, in the dorsal nucleus of the vagus nerve, and the nucleus ambiguosus.
And what kind of control does the vagus nerve have? What's its territory?
Its long preganglionic fibers project to terminal ganglia that control, well, almost every major organ from the neck down. It slows the heart, constricts the bronchi, and controls the esophagus, stomach, liver, pancreas, gallbladder, the entire small intestine, and even the first part of the large intestine.
That is an astonishing amount of real estate for one nerve. So how are the postganglionic fibers distributed across that huge area?
Well, those postganglionic fibers are short, and they're often woven directly into the organ structure. They create these vast local networks. So in the digestive tract, for example, they form what's called the mesenteric plexus.
A plexus, so a web.
A web of nervous tissue right in the organ walls that controls local movement and secretions. The vagus nerve provides the central rest and digest command, but the local plexus handles the moment-to-moment decisions.
Let's just pause for a quick recap on the structure because this is key. Sympathetic. Starts in the thoracolumbar spine. It's short pre-long post. Ganglia are near the spine, and it's built for a massive broadcast.
And parasympathetic. Starts in the craniosacral regions. It's long pre-short post with ganglia right near or inside the target, and it's built for precision and recovery.
Okay, we've arrived at the synapse. The electrical signal has traveled down the wire, but to cross that gap, it has to communicate chemically. It needs a neurotransmitter.
Correct. The electrical impulse triggers the release of a signaling molecule. And we basically have two types of fibers based on the chemical they release. We have cholinergic fibers, which release acetylcholine, or emeric.
Okay.
And we have adrenergic fibers, which release norepinephrine or iperic.
Let's start with the cholinergic system, the one that uses AAO. Now, this chemical seems to be the starter for everything. So how can one chemical do such different things, like firing up the whole body or activating rest and digest?
The function of the chemical depends entirely on the receptor it binds to.
The lock determines what the key does.
Exactly. And the cholinergic system has two major types of locks, the nicotinic receptor and the muscarinic receptor.
Let's look at the nicotinic one first. What kind of lock is that?
It's a ligand-gated cation channel, which is a technical way of saying it's a doorway that snaps open the instant the chemical, the ligand, AGH, binds to it. When it opens, positive ions rush in, and the cell instantly depolarizes. It fires off its own electrical signal.
And this is the universal on switch, right?
Yes, this is a core rule of the ANS you have to remember. Nicotinic receptors are found on all ganglionic neurons. It doesn't matter if it's a sympathetic chain ganglion or a parasympathetic terminal ganglion. The preganglionic fiber always releases HE onto a nicotinic receptor to kick off the next step.
Okay, that covers the connection between the two neurons. What about the final destination for the parasympathetic system that uses the other one, the muscarinic receptor?
Right, the muscarinic receptor is a different kind of lock. It's a G protein-coupled receptor. When HE binds to this one, it doesn't just snap open a doorway.
What does it do?
It starts a much slower, more complex cascade of chemical changes inside the cell. It takes longer to get a response, which makes sense for the slower processes of, digestion and rest.
And this brings us to that really great analogy that explains where they got their name.
Exactly. So if AT is the master key that can open both locks, researchers needed specific keys to test each lock individually. They found that nicotine, the chemical from tobacco, binds perfectly and only to the nicotinic receptor, hence the name.
And muscarine.
Epoxin from certain mushrooms. It binds specifically to the muscarinic receptor. So the master key, AT-IC, opens both doors. But this confirms that vital point. The first step in all autonomic communication is the rapid firing of a nicotinic receptor by AT.
Okay, so if the parasympathetic system finishes its job by releasing AT-IC onto a muscarinic receptor, what chemical does the sympathetic system use for its final output? This must be the adrenergic system.
The adrenergic system uses norepinephrine and epinephrine, and these bind to a family of G protein-coupled receptors on the target organs called the alpha and the beta adrenergic receptors.
And there are subtypes, right? Alpha 1, alpha 2, beta 1, beta 2. That seems like a lot of detail, but I assume it's really important for how drugs work.
Oh, it matters tremendously. For example, beta 1 receptors are found mostly in the heart. When norepinephrine hits them, it increases heart rate and force. But beta 2 receptors are all over the bronchioles in your lungs and the blood vessels in your skeletal muscles.
And what happens there?
When epinephrine hits a beta 2 receptor, it causes them to relax. So you get bronchodilation, more air, and vasodilation, which is more blood flow to your running muscles.
So the sympathetic system isn't always about constricting and speeding things up. It's about getting resources exactly where they're needed for survival.
It's strategic mobilization.
Yeah.
But the main output molecule from most sympathetic postganglionic fibers is still norepinephrine. That's what drives the overall acceleration and, specifically, the constriction of most of your systemic blood vessels via the alpha-1 receptors.
Now we have to talk about the big exception, the one that messes up the chemical map.
Yes, this is a classic exam question. It's designed to check for deep understanding. Sympathetic fibers that project to two specific places, your sweat glands and the blood vessels in your skeletal muscle, do not release norepinephrine.
What do they release?
They release AA onto muscarinic receptors.
So you have a sympathetic origin thoracolumbar spine, but a chemical output that looks parasympathetic. Why the confusion?
It just reinforces the rule that we define the system by its anatomical origin, TL, not its final chemical. The sympathetic system needs you to sweat, and it needs those muscle blood vessels to dilate during fight or flight, even if it uses an unusual chemical to do it.
Let's quickly clarify the names. Adrenaline versus epinephrine, are they the same thing?
They are the exact same molecule. The names just come from different language roots. Adrenaline is from Latin, adrenal, meaning on top of the kidney.
Right.
Epinephrine's from Greek, epinephrine, meaning above the kidney. We use epinephrine in science, but it's the same stuff.
And what's the difference between calling it a neurotransmitter and a hormone?
It's all about the delivery system. When norepinephrine is released by an axon directly into a synapse, It's a neurotransmitter.
Yay.
But when that exact same molecule, along with epinephrine, is released by the adrenal medulla into your general circulation, traveling through the blood, we call it a hormone.
Same chemical, different job title, depending on how it travels.
Perfect analogy.
And just one last note on structure. The autonomic synapse isn't the typical little knob at the end of a nerve, is it?
That's right. Autonomic postganglionic fibers don't usually end in one neat little terminal bulb. Instead, they have a chain of small swellings along the fiber called varicosities. Each one acts as a little release point.
So instead of a precise one-to-one connection, it's more like a chemical spray.
Exactly. It's a diffuse network. And that's essential for controlling large areas, like a whole sheet of smooth muscle or a big gland.
Okay, we've laid out the wires and the chemicals. Now let's see how this all works in real time, through involuntary actions. Let's talk about the visceral reflex arc.
The visceral reflex is the mechanism of action. It follows the same basic pattern as a somatic reflex. You have sensory input, an integration center, and motor output. But the output branch is the key difference.
Right, if a somatic reflex is just one motor neuron hitting a skeletal muscle, the visceral reflex output has to be that two-neuron system we've been talking about.
Correct. The efferent branch is always the preganglionic fiber relaying through a ganglion, which then uses the postganglionic fiber to reach the effector, the heart muscle, smooth muscle, or gland. Always that two-neuron chain.
And what's the sensory input for these reflexes? We aren't aware of most of the data our body is collecting.
Most visceral senses are unconscious, but they're absolutely fundamental for homeostasis. A perfect example is the baroreceptor.
Baro, like barometer for pressure.
Exactly. These are mechanoreceptors in your aorta and carotid sinuses that are sensitive to stretch. They measure changes in blood pressure. So when your blood pressure drops, the signal from the baroreceptor instantly triggers a visceral reflex to constrict vessels or speed up your heart.
Sometimes, though, that internal sensation does rise to conscious awareness, but it gets projected to a completely random part of the body. That's referred pain.
Referred pain is a fascinating physiological glitch. The brain is trying to interpret intense visceral pain-like from the heart. But because the brain's map for internal organs is much less detailed than its map for the skin, it misinterprets the source.
Which is why a heart attack can feel like pain in your left arm or shoulder.
Precisely. The visceral sensory fibers from the heart enter the spinal cord at the same level as the somatosensory fibers, the normal touch and pain fibers, from the left arm and shoulder. The brain gets the signal and just defaults to thinking it's coming from the more familiar superficial area.
To make this really clear, let's go through that detailed example of Kerr's sign. That's when pain from a ruptured spleen is felt in the left shoulder and neck.
This is a superb example because it seems so counterintuitive. The spleen is in the upper left abdomen. Its sympathetic nerves come from the mid-thoracic spine. Logically, the pain shouldn't be referred way up to the neck.
So why does it happen? The sympathetic pathway doesn't explain it.
No. The crucial insight is that the sensation isn't coming from the spleen itself. It's coming from the diaphragm.
The diaphragm, the breathing muscle.
Yes. When the spleen ruptures, blood pools in the abdomen and puts a lot of pressure on the underside of the diaphragm, causing irritation.
And the nerve that senses that irritation is the key.
Exactly. The diaphragm is innervated by the phrenic nerve, which connects way up high, entering the spinal cord to the mid-cervical levels, C3, C4, and C5.
And where do the pain fibers from the skin of the shoulder and neck enter the spinal cord?
Also at C3, C4, and C5. The brain receives a pain at C3, C5 message, and because it's used to that signal coming from the shoulder, it interprets the diaphragmatic pain as shoulder pain. It's a perfect case of sensory crosstalk.
That makes so much sense. Okay, let's categorize these reflexes. We have long reflexes and short reflexes.
A long reflex is one that involves the central nervous system. The sensory input travels all the way to the brain or spinal cord. That's where the decision is made, and then the two-neuron motor pathway is activated.
And a short reflex is the local short circuit?
Exactly. A short reflex is completely peripheral. It bypasses the CNS entirely. The sensory input gets integrated directly within a peripheral ganglion, which then initiates the motor output. It's incredibly fast and local.
And the ultimate example of this is the enteric nervous system.
The enteric nervous system, yeah. It's often called the second brain. It's the web of nervous tissue, the myenteric plexuses, embedded right in the walls of your digestive tract. So if stretcher receptors in your stomach wall detect a big meal, a short reflex in that plexus can immediately cause muscle contraction to increase motility and start digestion,
Oh.
all without bothering the brain or spinal cord.
So the vagus nerve provides the overall influence, but the enteric nervous system handles the local logistics. A very efficient division of labor. So the central function here is this continuous, subtle competition between the two divisions. And this active balance is what defines an organ's autonomic tone.
Autonomic tone, yes. It's the continuous influence that one division has over the other at rest. It sets the baseline activity. It ensures that systems are ready to react immediately, to go up or down when needed.
Let's start with a classic example. The heart. What's its dominant tone?
The heart muscle itself has an intrinsic rhythm of about 100 beats per minute. But your resting heart rate is much lower, maybe 60 to 80.
Right.
That slowdown is because the heart is constantly under strong parasympathetic tone from the vagus nerve. The parasympathetic system is actively braking the heart.
Now what about our systemic blood vessels? What's their tone?
This is a critical point. Systemic blood vessels are almost entirely under sympathetic tone. The sympathetic system maintains a baseline, slight level of constriction in the vessel walls, which is essential for maintaining blood pressure.
And the parasympathetic system has almost no say in this.
Almost no influence at all on the widespread circulation. So if you feel stressed and your blood pressure goes up, that's entirely the sympathetic system activating further. There's no parasympathetic system that can globally force your blood vessels to dilate.
Which is why stress management is so important for cardiovascular health.
Exactly. If that sympathetic input is unopposed, it drives high blood pressure. When the sympathetic system releases more norepinephrine, the vessels tighten. When it releases less, they passively relax. The sympathetic tone is the dial for blood pressure.
Let's look at a clinical example of this in action. Orthostatic hypotension. That's the head rush or dizziness you get when you stand up too fast.
That feeling is your sympathetic system scrambling to save you from fainting. When you stand up, gravity immediately pulls 500 to 700 milliliters of blood down into your legs and abdomen. That causes an instantaneous drop in blood pressure to your brain.
And the reflex that stops you from passing out.
So the change in posture is sensed by proprioceptors, and the drop in pressure is detected by those baroreceptors. That signal flashes to the CNS. The CNS immediately activates the sympathetic division in the upper thoracic spine, and that output uses cardiac accelerator nerves to speed up the heart and vasomotor nerves to rapidly constrict the blood vessels.
So faster pumping and tighter pipes pushes blood back up to the brain.
That's the goal. Orthostatic hypotension happens when that sympathetic reflex fails. It could be due to hypovolemia, just not having enough blood volume because you're dehydrated.
Or something more serious.
Or, more seriously, it could be due to underlying autonomic failure, like nerve damage from advanced diabetes, where the sympathetic fibers just can't execute the command to constrict the vessels.
We've seen how the reflexes work moment to moment, but there has to be a master coordinator in the brain setting the overall strategy. That has to be the hypothalamus.
The hypothalamus is absolutely the master control. It sits at the nexus of the nervous system and the endocrine, or hormonal system. It is the central integrator for pretty much every homeostatic mechanism: temperature, thirst, hunger, sleep, and critically autonomic balance.
Let's use the pupillary reflex to see how it integrates external data.
Sure. So when bright light hits your retina, the signal travels along the optic nerve. The main pathway goes to your cortex for conscious vision, but a side path splits off and goes directly to the hypothalamus.
And the hypothalamus just interprets the light intensity.
It immediately initiates the correct involuntary response. So highlight means it drives the parasympathetic output to constrict the pupil. Low light, it stimulates the sympathetic neurons to dilate the pupil.
And how does the hypothalamus send these commands down to the lower brainstem and the spinal cord?
It uses two main fiber pathways that run down through the brainstem: the medial forebrain bundle and the dorsal longitudinal fasciculus. These are the highways that let the hypothalamus influence all those lower centers.
Now, let's connect this to emotion. This is where the ANS really impacts our daily lives. Why does anxiety immediately give you a racing heart?
That link is managed by the limbic lobe, which is all about emotion and memory. And the key structure for generating fear and anxiety is the amygdala.
And the amygdala speaks directly to the hypothalamus.
It does. When the amygdala senses a threat real, or just perceived, it sends potent distress signals down to the hypothalamus. The hypothalamus interprets this emotional distress as a biological emergency and just hits the big red button for the entire sympathetic fight-or-flight response.
Which gives you the racing heart, the sweating, all of it.
All of it.
Moving down the brainstem, we get to the medulla. And this houses the truly vital autonomic centers.
Yes, the medulla is essential for survival. It has the cardiovascular center, which directly controls the circulatory system. If the medulla shuts down, life stops.
How does it manage sympathetic control of the heart?
It has nuclei that send signals down to the upper thoracic spinal cord. When blood pressure needs to go up, the medulla uses those cardiac accelerator nerves to speed up the heart and the vasomotor nerves to constrict vessels.
And for parasympathetic control?
For that, it relies on two major nuclei that contribute to the vagus nerve: the dorsal motor nucleus of the vagus and the nucleus ambiguus. These nuclei are constantly firing to maintain that parasympathetic tone on the heart, keeping the rate down, and also managing signals for digestion.
Understanding all these specific receptors and chemicals is so vital for medicine because it lets us precisely manipulate the body's internal workings.
It does. And when we talk about drugs, we need to classify the chemicals. An endogenous chemical is one your body makes, like Ablashi. An exogenous chemical is one from the outside, like a drug or a toxin.
And they either mimic the natural chemical or they block it.
Exactly. A drug is an agonist if it mimics the effect of the endogenous chemical. It's an antagonist if it blocks the binding site and produces an opposing effect.
Let's start with a really potent agonist we all know, nicotine. It's a nicotinic agonist, so it hits that universal starter button.
Right, and because those nicotinic receptors are on all preganglionic fibers, both sympathetic and parasympathetic, nicotine just activates both divisions at the same time. It's massive system-wide excitation.
And while that might sort of cancel out in the gut, it's catastrophic for the cardiovascular system.
Two major risks. First, since there's no parasympathetic brake on your blood vessels, the increased sympathetic output is completely unopposed. That causes sharp and chronic hypertension, high blood pressure.
And the second risk?
The heart muscle gets simultaneous conflicting go and stop signals. This doesn't just cancel out, it messes up the rhythm, leading to arrhythmias or irregular heartbeats. Both are huge drivers of cardiovascular disease.
Let's move to therapeutic drugs. The ones targeting the sympathetic side, the adrenometic system.
Okay, so drugs that enhance sympathetic function are called sympathomimetic drugs.
Sympathone, mimetic. So they mimic the sympathetic system.
Exactly. A common example is the decongestant phenylephrine.
How does that work?
It's an alpha-1 adrenergic agonist. It stimulates the alpha-1 receptors on the smooth muscle of blood vessels, causing them to constrict. In your nasal passages, that shrinks the swollen blood vessels and clears your sinuses.
And what about indirect ones like caffeine and cocaine?
So this is where it gets interesting. They don't bind to the receptor, but they boost the effect of your natural chemicals. Caffeine, for example, blocks a chemical called adenosine, which normally inhibits the release of norepinephrine.
So by blocking the inhibitor, you get more stimulation.
You get more norepinephrine release, more alertness, higher heart rate. Cocaine is different. It blocks the reuptake pump that normally sucks neurotransmitters back up into the nerve terminal. So the neurotransmitter stays in the synapse longer, keeps stimulating the receptors, and causes a massive sympathetic rush.
Okay, now the drugs that interrupt the sympathetic system, the sympatholytic drugs.
These are antagonists. They block the adrenergic receptors. The most common are the beta blockers, like metoprolol. By blocking the beta-1 receptors in the heart, they reduce cardioacceleration. They're used all the time to treat heart conditions.
And for anxiety, too.
Yes, because they block the physical symptoms. If your amygdala signals for fight or flight, a beta blocker stops your heart from racing and your hands from shaking. It mitigates the physical panic.
Switching to the other side, drugs that enhance cholinergic effects are parasympathomimetic.
Right, they enhance rest and digest. A key example is pilocarpine, which is used to treat glaucoma. It's a muscarinic agonist that causes the pupil to constrict, which helps drain fluid from the eye and reduces pressure.
And finally, the blockers, the anticholinergic drugs.
These are muscarinic antagonists. The most famous are atropine and scopolamine from the deadly nightshade plant belladonna. Atropine is used in emergencies to rapidly increase a dangerously slow heart rate by blocking the vagus nerve's braking effect.
And we know historically belladonna was used cosmetically to dilate pupils.
Exactly. By blocking the parasympathetic constriction, it lets the sympathetic system dominate and the pupil gets bigger. But systemically, it's deadly because it shuts down all parasympathetic functions.
How is scopolamine used to treat motion sickness? That seems counterintuitive. You're blocking rest and digest to stop nausea.
While motion sickness is an autonomic crisis, it's triggered by a sensory mismatch between your eyes and your inner ear. This conflict is processed in the brainstem, near the vomiting center and the vagal nuclei. The symptoms? Nausea, cold sweats are all acute autonomic responses. Scopolamine, as an Cholinergic just reduces the parasympathetic activity that's driving those symptoms. It calms the system down.
We have completed a pretty comprehensive tour of the body's ultimate control system. Let's try to consolidate the key takeaways for everyone listening.
Okay, first the structure. Just remember the basic fight. The sympathetic is the widespread thoracolumbar system, short pre-long post, built for speed. The parasympathetic is the precise craniosacral system, long pre-short post, and it acts as the brake.
Second, the chemical role. Acetylcholine, or AC, is the universal master key. It starts every relay by binding to nicotinic receptors on the ganglia. The final signal depends on the mission. Sympathetic usually uses norepinephrine for acceleration, while parasympathetic uses AC on muscarinic receptors for braking.
And third, the higher control. Homeostasis is maintained by this balancing act, this autonomic tone. The hypothalamus is the master coordinator, integrating emotion and sensory input. And the medulla holds the vital moment-to-moment control of your cardiovascular system.
All right, time for a quick quiz. Let's see what's stuck.
Let's do it.
First question. If a patient is given phenylephrine as a decongestant, which division of the ANS is being mimicked and why?
That would be the sympathetic division. Phenylephrine is an alpha-1 agonist causing constriction of blood vessels, which is the same action the sympathetic vasomotor nerves use to raise blood pressure.
Perfect. Which type of preganglionic fiber is typically the longest? Sympathetic or parasympathetic?
Parasympathetic. Those fibers have to travel all the way from the brainstem or sacral spine to the terminal ganglion, which is right near the target.
Okay, if you're feeling intense pain from an organ like the gallbladder, but you feel that pain in your shoulder blade, what's the term for that phenomenon?
That is referred pain. It's caused by the visceral sensory fibers entering the spinal cord at the same level as the somatosensory fibers from the shoulder.
Which signaling molecule is primarily responsible for that dramatic increase in heart rate during a sudden threat?
That would be epinephrine or adrenaline, released as a hormone from the adrenal medulla.
And last one, what is the term for the default state where your blood vessels are kept in a state of slight constriction by the sympathetic division?
That is sympathetic tone.
Fantastic. You now have a solid working knowledge of the subtle, powerful autopilot running your life.
And that leads us to our final provocative thought. The name sympathetic comes from Greek roots meaning suffering together. This wiring is ancient. It's geared entirely towards surviving a physical emergency. What does it actually mean for our long-term health, for our homeostasis, that this massive survival mechanism is now being triggered daily by the abstract stresses of modern life?
We're constantly hitting the nitro button for threats that never require us to physically run away. What is the chronic, long-term impact on our health when we live in that perpetual state of low-grade emergency? It makes you think that maybe the most urgent thing we can do is find a way to intentionally activate that parasympathetic brake.
A profound point to end on. Thank you for joining us for this deep dive into the autonomic nervous system.